Bismillahirrahmanirrahim. This is probability and statistic course for civil engineers, civil engineering batch F18. The topic today is Poisson distribution. This is lecture number 9. We have already discussed about other distributions that are binomial distribution and constant distribution. So this is another probability distribution, which is basically discrete probability distribution. So I will talk about the probability equations, and I will also talk about some example. Now, what is Poisson distribution? Poisson distribution is a discrete distribution, probability distribution for the counts of events that occur randomly in a given interval of time. So we will determine the probability of occurrence of different events in a given interval of time. Many experimental situations occur in which we observe the count of events within a set of time, area, or maybe volume, length, etc. For example, number of cases of disease in different time, or we want to check the probability of number of vehicles at a toll collection plaza in 1 hour, or maybe number of students entering in a class in 5 minutes. So what is the probability of entering of 5 students in a class in 5 minutes? What is the probability of entering of 4 or 5 vehicles in 1 minute at a toll collection plaza? So for all these we have to use the Poisson distribution. And as I said, number of cars, number of people, number of students, number of cases of disease, so that are related to the discrete data. As I said, Poisson distribution is a discrete distribution. The discrete random variable x may be 0, 1, 2, 3. That will not be 0, 0.5, 1.5, 2.5. That will be a whole number that will have a value equal to 0, 1, 2, 3, not 1.5. Number of entities, number of anything, number of cars, people, or number of disease, all are random. We can't say 1.5%, we can't say 2.5%, we can't say 1.5 people or 1.5 cars. So that random variable x will be equal to 0, 1, 2, 3, 4 till n. We also have a parameter, same like if we see here, the parameter that is an average value lambda, and that is a parameter for Poisson distribution, same like a parameter we had for binomial distribution, and NP were the parameter for binomial distribution. Similarly, A and B were the parameters for constant distribution, and only a single value, that is lambda, is parameter for the Poisson distribution. What basically is lambda, I will talk about that later in further slides. So the probability value for any random variable x, that will be given by this equation. That is an equation for the, if you see here, that is an equation editor, and for any value of random variable x, that might be 0, that might be 1, that might be 2, we can input in we can embed or input these random variable values, and then we have this equation. This is the equation for the Poisson distribution. Is exponential, that is 2.718 is the actual value of e, power lambda, that is the parameter, then multiply by lambda power x. X is random variable, you can see x is equal to 0, 1, 2, 3, and then in the denominator that is x factorial. X factorial, you know that x factorial is basically x factorial is actually sorry, that's some problem. Okay, x is equal to x multiplied by x minus 1, and then multiply by x minus 2, so that will go toward 2, 1, and then 0. So you know about that factorial term. Now coming toward the slides. Okay, so e is 2.718, that is natural number x, e power ln x, and we can also represent that Poisson distribution for any random variable x and as I said, random variable can be any parameter of interest. For example, if we are determining the we are interested to determine the number of cars, so we will have x is equal to 0, 1, 2, 3. That will actually represent number of cars. Then that will be Poisson distributed with the parameter lambda. So as I said, we can represent it like this. Now mean and standard deviation are another two important features for any distribution. So mean of a Poisson distribution, that is expected value, or mean of the Poisson distribution, mu is equal to lambda, that is simple lambda. And same the variance for, as we have discussed for other distribution, variance is equal to lambda. So it's very easy for Poisson distribution that mean and variance of the Poisson distribution are equal to lambda. Now if we have this distribution, let's have some examples related to that. For example, births in a hospital occur randomly at an average rate of 1.8 births per hour. If we have a time interval of 1 hour and we are going to determine the probability of what is the probability of observing 4 births in a given hour at the hospital. So if we are going to determine the probability of 4 births in an hour, if we have the average rate of birth, that is 1.8 births per hour. So lambda is basically that 1.8, the average value. If we go to our previous slides, so lambda is actually the average value of rate. So if you see here in this equation, in this example, average rate of births, that is 1.8 birth per hour. As I have already mentioned to you that average value can be in decimal, not the discrete value, but the average can be a decimal value. So if we solve this equation, we can if we solve this problem, we can use same equation, that is probability of x for any random value. Here x, we will replace it by 4 because we are going to determine the probability of 4 births, and we can use the same equation. If we if I minimize and if I keep it to the side, so the probability of that p of that x is equal to 4, and that is equal to, so we will use that equation. So e is same e, that is 2.718 to the power we have average rate, that is equal to 1.8, so that will be minus 1.8, and then multiplied by lambda, that is also, so multiply by lambda, that is also 1.8 to the power x. So x here is 4 to the power 4, and then divide by 4 factorial. So by solving this equation, that will give you the probability of x is equal to 4. So that the Poisson distribution is a simple one. If they also ask you what is the mean and standard deviation of probability Poisson distribution, if you have average rate of birth 1.8, so as I have already discussed in my previous slide, that the mean of Poisson distribution is equal to its lambda, and variance of Poisson distribution is equal to its lambda. So as I said here, lambda, that lambda is equal to 1.8, so that is also the mean of that distribution, and that is also variance of that distribution. Now let's come toward another example. A typist makes an average 2 mistakes per page. What is the probability of a particular page having no error on it? So no error means if he's making mistakes, 2 mistakes, 3 mistakes, 4 mistakes. But if we talk about 0 error, so it means there is no mistake. So the probability of 0 mistake, that will be equal to probability of x is equal to 0. So starting with x is equal to 0, and since he's making 2 mistakes per page, so lambda is equal to that lambda is actually that. So x value is 0, so same, I will embed e 2.718 power lambda, that is 2, and then 2 power 0 and 0 factorial, because we are going to check the probability. Now we are going to determine the probability of 0 errors. So after solving this equation, you will get the probability of 0 error or probability of no error. Okay, so we have already discussed 2 examples. Let's come toward another example. That's not in fact example number 2, that is example number 3. I'm not going too much into detail because it will be difficult for you if I start explaining some more terms related to the Poisson distribution. So I'm just trying to explain in the easiest way the Poisson distribution, and I will also use an Excel to guide you how to determine the Poisson distribution values in Excel and how to develop a graph in that. So let's talk about another example. Suppose the number of snake bites cases seen in an year has a Poisson distribution with the average 6 bites cases. So at an average 6 bite cases, so that 6 is actually lambda value. What is the probability that in 1 year, the number of snake bites cases will be 7? So we need to determine probability of x is equal to 7. Same, the number of snake bites cases will be less than 2. So the probability of x, so the probability of x equal to 7 and the probability of x smaller than 2, we are going to determine these 2 values. Now the random variable, that is x, which is number of snake bites cases in a year, so lambda value is 6. X is Poisson distributed with the lambda equal to 6. Now if we have x is equal to 7, so we can see here that equation here we can see probability of x is equal to 7 e power minus 6, because that 6 is lambda, so lambda power 7, that lambda power x, so x is equal to 7 and 7 factorial, so that will give us 0.137. so there is a probability of 0.13 that number of snake bites in linear cases will be 7. Now, so the another one is when x is equal to 2. So x is equal to 2 means probability of x is equal to 0 plus probability of x is equal to 1. We will not have a probability of x is equal to 0.5 or x is equal to 0.75 because these are all whole numbers. So we will take only those numbers. We will take only whole numbers that are x is equal to 0 and x is equal to 1. So for the probability of x minus 2 is actually the probability of x is equal to 0 plus probability of x is equal to 1. So if x is equal to 0, we will use the same equation with replacing x with 0. So you can see here 0 and 0 factorial, similarly plus probability of x is equal to 1, so that is e power minus 6 multiplied by x power 1 divided by 1 factorial. So that will give us the probability of x smaller than 2. So you can also compute what is the probability that in 2 years there will be 10 bite cases. What is the probability then in month there will be no snake bite cases. So okay, if we see here number of snake bite cases in 2 years, for 1 year the average was 6. So for 2 years lambda will be modified and that lambda star equal to 2 multiplied by 6, because now mean for the 2 years is 12. Mean for 1 year was 6 and mean for 2 years is 12. So using the same technique we will be having probability for different values. Okay, if we talk about for a month, that was the previous one was for 2 years and now it's for 1 month. So we have 12 months in an year, and if we check for 1 month, so we will modify lambda and that lambda will be replaced. Lambda will be equal to lambda by 12. So 6 was the average for 1 year divided by 12 and that will give you 0.5. So now lambda which is the average parameter for Poisson distribution for 1 month, that is equal to 0.5. And using same procedure, we can determine the probability value. Now there is one example. You can solve it at your own, and I will just show you how to develop probability distribution diagram. So let's see in an Excel. If we have X values, I will write it here. If we have X, okay, so X value, and we have B here, that is giving you the probability of X. So using different value of X, let's just start with 0, then 1, then 2, then 3, then 4, and coming towards maybe, okay, 12. So if we have X values starting from 0 to 12, Px, we have embedded equation in Excel for the Poisson distribution, but as I said, we need to have lambda value. So if I say lambda, that is equal to, if I say lambda that is equal to, let's assume that, okay, 0.75. Let's say I have a parameter, average parameter value, lambda is equal to 0.75 for the Poisson distribution. So if I start determining the probability, instead of using that equation, we have in Excel embedded equation. So is equal to the Poisson, I will select that Poisson distribution, okay, X value for a Poisson distribution, I have starting X value starting from 0 till 12. So first one, X is 0. Then I'll say another one, that is mean I have 0.75. so I have to fix that 0.75, and for fixing that 0.75 I will use the $2 signs, one here and another one here. Cumulative, we are not going to determine the cumulative probability distribution, just the probability distribution of Poisson. So we are not going to determine that. We just need to determine the probability mass function or probability density function of Poisson distribution. So we are not interested in cumulative this time. We are interested in probability mass function. So you can write false here. Okay, close the bracket, and that will give you the probability value of X is equal to 0 when you have lambda value 0.75. So you can drag it till 12, and that will give you the probability value for each random variable. Now you can plot a graph. If I insert graph here in column graph, so you can see here that the trend is a kind of decreasing trend. In probability, normally we have in a Poisson distribution, we also sometimes have a graph that is increasing, and then after increasing it decrease, it's like a skew toward the right. So here we can see that if we have lambda value 0.75, if we have X value 0 to 12, so we will be having different probability values. Let me change the lambda value and see how the graph value changes. Let me have lambda that is equal to let's make it 2. So if we have 2, you can see the graph changes. It's also showing some smaller values at the left side, and then increasing and then decrease. So 1 is smaller than 2, and then there is almost same graph for 2 and 3, and then there is a decreasing trend. Let's see how about 3. If lambda average value is 3, so if you see that average value 3, so average will fall somewhere here. If you see that is 3, so most of the data is lying here. And as I said, if we have 0.75, so most of the data is falling somewhere here in this region. So lambda value, that the average value of Poisson distribution, the mean value of Poisson distribution is actually representing its shape. Its shape varies with different values of lambda. Now you also can increase that value from 0.75, let's say 5. If we have 5, you also know that lambda is also the mean of Poisson distribution. So in making it 5, we will be having more data here. If I click that, so you can see here more data falling somewhere 5 and 6. So lambda is increasing, lambda is actually changing the shape of that Poisson distribution. So now you know about the Poisson distribution. That is basically a very simple probability distribution. We have some advanced level or modified version of Poisson distribution, but as this is a basic course of probability and statistics, so that was all related to the Poisson distribution for batch F18. Thank you so much for this. I will talk about exponential distribution in next lecture.